now we have to go through some list of 3 regions. And the other problem is that it still can trigger a compacting phase if it runs out of 3 regions. But there are some good words about it, that it actually runs pretty nicely with really short garbage collection poses, and if you have the settings nicely, then it will not run out of 3 regions as well. So a new development, which was just recently announced, is a garbage-first garbage collection. So it's a pretty neat idea. What basically they did is that it's kind of a usual mark compact, but like with previous mark compacts, usually the heap was separated in some specific generations, like Eden, like what was it? What? Yeah, Tenor, yeah, exactly. Like Eden, Tenor, and then like 2 survivors usually. So instead of that, garbage first separates the heap into equal regions, many equal regions, and it has a neat idea that during the allocation, it tracks during the kind of the time when the program is running, it tracks which regions, how much garbage is in each region. So it kind of has a good estimate how much garbage is in each region, which means that when you trigger garbage collection, then then usually garbage collection, it tries to estimate how much memory will you need. So maybe you need 100 megabytes. It's not terribly hard to estimate because it tracks the average allocation rate and basically looks like how much memory you probably need. And what it does is that it will only garbage collect a few regions, like so that it will estimate how many regions it needs to collect to free that much memory, and it will only garbage collect those regions. So it's a pretty neat idea. Unfortunately, it's also a bit of a trade-off, because what happens is that to be able to track the regions, which regions are garbage or not, it needs to track references between the objects, so it separates also, and between the regions, so it also separates the regions in smaller regions called cards. And what it does is that every time you assign a value, every time you assign a reference, it will have a few instructions, which basically is called what is called the write barrier, which will kind of update that there's a reference from this card to that card, and then it will basically in live it will track which cards are garbage and which cards are not garbage. But it's a trade-off because the assignment is now more expensive, right? So the previous garbage collection was trading off on allocation. This one is trading off on assignment, and it's a very neat idea because in some cases it's better. Not in all of cases, but in some cases it's better. So the final garbage collection algorithm, which I'm going to talk about, is called Azul Pauseless. It's actually a different Java virtual machine. It's a Java virtual machine by Azul, which is called Zing, which only runs on Linux if you install certain kernel models to it. And it had some, it's like right at the moment it's kind of the coolest one out there for many different reasons. So one of the things that it does the same regioning that the garbage first does. It does it a bit differently with a little less cost on the, as far as it's done, with a little less cost on the write barriers. So that's one of the things, but a more important thing it does is that it's actually a fully concurrent mark compact sweep, which means that the marking, the relocation, and the remapping all run concurrently with as many threads as you have parallelly to your application, which is a pretty neat achievement. And the way they do it is actually by using, and here we return back, by using the page table. So here's an interesting thing. A couple of years ago, there were new extensions introduced for memory virtualization, right? So for years, the guys who virtualized, like VMware and so on, they were crying foul for actually Intel because there was like one huge problem that they needed to, we have a host operating system, we have many guest operating system, and the thing is that guest operating system, they all have their own page tables. But there was no way in hardware to have multiple page tables, you could only have one. So what happened is that the page table in the guest operating system, they were binary patched, like these places where they were accessible binary patched, and they were kind of emulated in software, and this was incredibly expensive. The majority of the overhead, like in the guest OS, would be this emulating in software those damn page tables, because everything uses them, right? Everything uses them for any access to memory. And because like usually everything, all the page table stuff, it's all in hardware. It's not in OS actually. There's a TLB, like table something buffering, right? forgot what it exactly stands for, but which is in hardware and which does all this page table translation. Yeah, okay. And and what was introduced is that you can have multiple page tables, you can have multiple TLBs, and what Azul uses it for is that they say, okay, so let's map two page tables to the Java heap, like split it in, and basically take it one page at a time. Let's make big pages, and when we do, and what happens is actually that when we start, remember they also split the memory into regions, and when we start garbage collecting a region, when we decide, okay, we're going to start collecting this region, collecting all of this region, what we do is that we map a new page to it, so now it has two virtual addresses, and the old one is now invalid, the old one is now dirty, it will always cause a page fault, and we start relocating the objects, compacting them parallelly in the new one, so one at a time, we copy, 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 and if somebody tries to meet, and we don't, and at the same time we run in parallel this remapping all the time, we just throw somewhere that this object was updated, and the remap threads start going through they're all the time going through the objects, and now they're updating the things. So, and what happens if we try to update object in its old place is that because the old page is now marked as dirty, it will generate a page fault. And since, remember I told you that page fault is a generic callback, so Azul actually handles it themselves. And what they do is that they go back to the object and they update the reference in place and then retry the access. So this is a very, very neat trick. It's possible only because they actually have this kernel models loaded, because they have access to the page faults. And the very cool part about it is that they have remap, this map relocator and remap, mark relocator and remap running all in parallel with your, what they refer as mutated threads, so basically your usual application. And so this is the future, this is probably what one day will be also in the JVM, because this basically has no stop the world phase, and it just all runs concurrently, and if the only place where it could possibly stop the application if you're allocating memory faster than the algorithm can collect it, and that's just a question of tweaking the settings, I guess. Like what proportion of the time you want the garbage collection to spend, right, doing it. Okay, so this is mainly what I wanted to talk about. The Azul actually also has, a hardware machine, this Vega, where they have even more neat tricks. So there could be even more tricks we could bring into if we had the hardware support for them. But already there are some really awesome, directions that kind of solve a lot of those issues. And so this is pretty much it. Yeah, the only here the main takeaway is, besides this names of the algorithm and kind of generic idea, what they do is that to do really good GC we need, more hardware support, and now we actually have more hardware support, and we may be getting even more hardware support in the future, and now we're only waiting actually for operating system support, in a lot of ways. So here's the takeaway. You're always running in a distributed system. In fact, you are always running in a distributed system. And in fact, even if you don't think you're running in a distributed system, you're still running in a distributed system. And, well, we're waiting for the OS to catch up, but there's some really awesome stuff going in the garbage collection world. And you can mainly, for a lot of it, you can just take advantage right now. And thank you very much for listening. I hope you learned a little something. I hope that you got thinking a little bit. And thank you very much for listening.